Hello, I'm Pete Conrad, and I was commander of the Apollo 12 moon mission. And I'm here to fill you in on our space program's newest and most exciting mission, a revolution in the way we get to and from space. Our goal is to make access to space so cheap and routine that in your lifetime, we can open this great new frontier to people like you, and America can return to the moon, this time to stay. And this is the first step. It's called the Delta Clipper Experimental, or DCX. This machine is unlike any rocket ever built. It takes off and lands vertically, and it's the first in a series of test rockets that proves technology a step at a time, like we did with Mercury and Gemini before we flew Apollo to the moon. Only this time, the goal is cheap access to space. Here's the problem. Imagine if every time you flew from point to point, your airplane threw away most of its parts during the flight. That's exactly how most of the world's rockets operate, since they were conceived in an age before lightweight composites and other advanced technologies were discovered. It's also one major reason it's so expensive to do anything in space. The DCX is the first step in a new test program to prove the concept of single stage to orbit, or SSTO, which means one piece up, one piece down, like an airplane, eliminating the delay and high cost of putting the craft back together for each flight. And, as you can see by the size of our DCX ground crew, reusable rockets can be maintained by small numbers of people for low-cost operations. I'm sure you've seen the huge control center we used in Apollo and for the Space Shuttle. Well, this is the DCX Flight Operations Control Center. Inside, two of us fly the vehicle using this cockpit, which is modeled after our commercial aircraft displays, another part of our streamlined designs for operations. I say we fly, but in reality, the DCX is so automatic, it flies by itself. And here's an example. On flight number 5, an explosion of some ground equipment ripped a 4 by 15-foot hole in the side of the DCX during liftoff. The vehicle lifted off anyway and was flying its mission on track, demonstrating its robust design. As a precaution, I decided to execute the auto abort sequence, and the vehicle landed safely on the desert floor. If this had been an old-style rocket, it would have crashed or been destroyed, but the DCX demonstrated that SSTO technology allows you to save the vehicle and payload and then push on. On each of the 8 flights of the DCX, we pushed the envelope further and further, learning valuable lessons quickly and at a very low cost to the taxpayers. On the final flight of this series, we rotated the rocket into a nose-down position as if it were returning from space. Then we translated into a tail-first position as if it were preparing to land, a critical maneuver for the next major phase of SSTO development. Like the X-15 behind me, the DCX has made history, leading a revolution in rocket technology. The DCX has completed all of its test objectives on time and on budget. Now it will be modified for continued use as NASA's DCX-A testbed. It will be rebuilt and will fly again in 1996, testing new lightweight components and structures needed for the next and much larger experimental vehicle called the X-33. The NASA-sponsored X-33 is the most important step in the development of this technology for cheap access to space. The X-33 is a rugged, lightweight vehicle which will finish proving the concept of single-stage to orbit. It will fly in the spring of 1999, extending the envelope to near-orbital regimes, demonstrating hypersonic and transonic flight, thermal protection, and engine restart. Equally important, it will demonstrate the aircraft-like operations needed to achieve low-cost, full-scale launch systems. The Apollo program gave us a can-do ethic, a first taste of what we will encounter on this new frontier, and it taught us that space offers a whole new future for humanity. And the X-33 project will give us the tools to achieve this great tomorrow. The day when Americans are able to go into space themselves is only a few years away, as routine commercial spaceflight at last moves from dream to a reality. The moon. I've been there. It was super. Soon it's going to be your turn.
In August 1991, sponsored by the United States Department of Defense, McDonnell Douglas Aerospace was awarded a competitive bid to design and test a liquid hydrogen, liquid oxygen fueled, fully reusable, single-stage rocket system demonstrator. The result is the Delta Clipper Experimental, or DCX. The design of the DCX included all associated ground servicing, maintenance, and flight control systems. The flight demonstration program would show the aircraft-like operation, autonomous flight control, and low-speed handling characteristics of a vertical takeoff and vertical landing rocket ship. The Delta Clipper Experimental began with the rapid prototyping of a technically complex, one-of-a-kind system by a streamlined, integrated government industry team. It was flying in less than 2 years.
Filling drains closed. 10, 9, 8, 7, 6, 5, 4, 3, 2, start. We have ignition. We have liftoff. We have engine throttle up.
Testing of the DCX proceeded along the same lines as conventional aircraft flight testing, continually expanding the flight envelope to cover a new flight or control environment, reaching to discover the unknowns and answer the skeptics by providing real flight and operating experience. The Flight 1 objectives were very simple. Show that vertical landing on Earth works. 150 feet up, across 300 feet, and straight down to a soft landing.
Go on hover. Landing low thrust.
And it did work, even in the presence of 25-knot winds and gusts.
Landing high thrust. Acceleration ramp down. We got a touchdown. Touchdown. Wait on gear. Engine off. All right.
Flight 2 expanded the envelope.
10, 9, 8, 7, 6, 5, 4, start and check engines. 2, 1, launch and flight.
Increasing the altitude to 300 feet. Moving sideways with greater speed.
Landing low thrust. Landing Q limit.
And demonstrating control with another soft landing within 3 feet of the first flight.
Landing high thrust, cell ramp down. She's looking really good. -6, -4, -3.
Between and during flights, the 8-person ground and 3-person flight crews continually demonstrated that efficient aircraft operations are equally applicable to a rocket ship if it is designed properly from the beginning. For Flight 3, the DCX had to handle its first problem. Helium bubbles in the propellant lines caused the engines to power up with unequal thrust. The DCX tilted as it lifted off. The onboard controls instantly recognized what was happening and quickly straightened the craft. The DCX went on to complete its expanded flight envelope, traveling to an altitude of 1,200 feet then landing back on its pad again within 3 feet.
Seconds coming into 1,200 feet.
Flight 4 demonstrated the ability to reactivate the entire system and carry out a successful test after being shut down for 9 months.
500 feet.
It also continued the flight envelope expansion, flying to about 2,850 feet above White Sands at its fastest speeds to date.
Cell ramp down.
The landing pad, by the way, is just concrete, showing that rocket facilities can be simple.
Wait on gear.
The crew then prepared the system for the next flight and were ready to fly within 6 days.
EE, your bottle pressures are about 2,400 psi on both sides.
Okay, it looks beautiful sitting out there. We'd like clearance to send the crew in, please.
You have
20
probably
seconds.
noticed the white clouds surrounding the vehicle at times and blowing away in the winds. These clouds contain some of the hydrogen gas being vented as the DCX propellant lines are chilled down.
7, 6, 5, 4, start and check engines, 3, 2,
Just at the start of Flight 5, through a combination of unfortunate circumstances, some of this vented hydrogen gas ignited and went into what the engineers call a fast burn. This caused a large overpressure on the side of the DCX, which in turn ripped a hole in its outer skin just as it lifted off.
Webinar will end.
The DCX flew rock solid, but Pete Conrad, the flight manager, knew there was not supposed to be a hole in the side and commanded the DCX to go into emergency landing procedures, or auto land. The DCX took command, stopping its forward and upward flight, deployed its landing gear, and came back down to land in the desert.
Gears deployed. Rolling up.
They were unplanned demonstrations,
Wait on gear, engine shutdown.
but it was clear that rocket ships could be designed to withstand equipment failures, as in Flight 3,
The bird is still vertical.
or even the massive damage which occurred in this flight, and land safely, be repaired, then fly again. Flight 6 occurred less than a year after the Flight 5 emergency landing. Back on the flight program, the DCX completed the objectives of Flight 5, reaching a higher altitude of 4,350 feet while traveling up and sideways faster, and came down at close to 100 miles per hour. In addition, pitch-over maneuvers, along with the first use of differential throttling and global position satellite data, further expanded the DCX flight envelope. Flight 6 again ended with a safe, soft landing near the center of the pad.
4, 3, 2, 1. Mark, vehicle launching. And we have a good vehicle. Airborne for Alpha Charlie.
Flight 7 expanded the altitude, reaching 5,700 feet, and the flight maneuvering boundaries, carrying out a 75-degree reverse pitch-over maneuver. Full roll control was carried out with the gaseous oxygen, gaseous hydrogen reaction control thrusters, and extensive use was made of differential throttling of the main engines for directional control.
75 plus
The
120
DCX descended at a velocity of over 130 miles per hour, again slowing to land in the center of the pad at less than 4 feet per second.
plus 130.
Immediately following the landing, the crew rapidly prepared the DCX and ground support for its next flight, and could have flown Flight 8 that afternoon.
start and check engines, launch and flight.
Flight 8 completed the chapter on the low-speed handling qualities of the DCX.
Okay, we're at 200 feet.
It flew to an altitude of close to 10,000 feet before reversing its flight direction to begin flying back toward its landing pad, nose first, just as the full-scale rocket ship would when returning from a flight through space.
At Looking good. Out of 4.
A key objective of Flight 8 was to show the controllability of the vehicle as it rotated from its nose-forward attitude during flyback to a base-forward attitude for its vertical landing.
Going into the pitch program, looking good. All the way over. 10 degrees down. Coming back. Looking good. Looking good. We're landing low thrust. Landing Q limit. It's looking good. Out of 4,000. Out of 2,000. Out of 1,500.
As in previous flights, the DCX descended vertically to land in the center of the pad,
Landing high thrust.
heralding the successful completion of the DCX flight test program and the start of the NASA DCX-A program.
Okay.
The flights of the DCX, coupled with the streamlined ground operations, have provided convincing evidence that America's space program is ready to enter a new era, an era of reusable rocket ships for low-cost, safe, routine flights to, from, and through space. The DCX and DCX-A projects are proving we are ready to take the next step, the NASA X-33 program.